An estimated 1.6 to 3.8 million people will suffer a concussion in the United States each year, most of which are sports-related. A concussion is a type of mild traumatic brain injury that results in temporary unconsciousness. Concussions can happen to anyone, whether it is clashing heads with another player, getting into a car accident, or simply hitting your head on anything or anyone. Concussions can do some serious damage. But where does the most serious damage occur? The brain. The brain is made of mostly water and bathed in cerebrospinal fluid. It is composed of distinct regions, the cerebrum, brainstem, and cerebellum, with varying tissue composition, outer gray matter cortex, or deep white matter. Each region is composed of different tissues in distinct arrangements. Due to this complex neural architecture, it is expected that the regions will have distinct tissue properties, many of which are anisotropic. The brain has different mechanical responses depending on if impact occurs in the coronal, transverse, or sagittal plane. Each has a unique effect on the resulting deficits. We will focus on how both the gray and white matters are affected during a concussion. The brain's gray matter is made of non-myelinated, short axons found in the outer cortex of the brain. The neurons in this part of the brain are short enough so that the electrical signals do not degrade from the start of the cell body to the axon terminal. Therefore, no insulation or ion channel signal boosting is required. The primary thinking, perceiving, and cognitive functions of the brain happen in the gray matter. In contrast, the white matter is made of myelinated long axons which travel from the cortex to the spinal cord. Its axons have high fiber bundle arrangements and are found deep to the gray matter. These structural properties are responsible for white matter being stiffer than gray matter, making it more prone to deformation. The boundaries where gray matter and white matter come together are known as the gray matter-white matter interface. The density difference between the white and gray matter makes this area more vulnerable to stretching and damage, specifically in shear. These are the areas that are most prone to deformation. Trauma to the brain can occur in two ways: from direct physical contact to the skull, or inertial forces which both result with the brain bouncing around within the skull. Most concussion injuries are inertial at the moment of impact. Inertial forces can be further broken down into trauma due to linear acceleration, altering the brain's internal pressure, and into rotational acceleration, which results in deformation to the brain tissue, twisting the brain's axons and tissues. Concussions follow rapid rotational acceleration of the head, leading to shear forces acting on the brain. Due to this deformation, the brain tissue stress-strain curve shows nonlinearity, viscoelastic properties, and anisotropic behavior.
This bar graph summarizes the average shear stress at 50% strain of gray and white matter across varying strain rates. The x-axis displays strain rate and the y-axis displays shear stress at 50% strain. At higher strain rates, the shear stress increases for both the gray and white matter, while lower strain rates increases shear stress for white matter more than gray matter. As strain increases, there is a smaller difference in shear stress experienced by gray and white matter. White matter's highly organized axon fiber bundles make it stiffer than gray matter, which is made of cell bodies that are less organized than the axons in white matter. Greater organization of organic material leads to a stiffer biological tissue. A stiffer tissue is able to withstand higher stress during shear loading. Stiffness and strength are also greater under a higher loading rate. Stress-strain curves can also be used to analyze the different loading properties gray and white matter have under shear stress. Strain is on the x-axis and stress is on the y-axis. As seen with the previous graph, at higher strain rates, there is higher stress in gray and white matter. Even though the difference of stress the two matters could handle is smaller at higher loading rates, white matter is still stiffer than gray matter. Shear stress can be calculated mathematically to compare the effects of a concussion on white and gray matter. Because stress and strain are not uniform throughout the brain due to different fiber orientations, the torsional shear stress formula was used. Since most shear deformation occurs in rotational acceleration, there will be a twisting force. Shear stress equals twisting moment times the radius, divided by the polar moment of inertia. In order to solve for shear stress, First solve for the polar moment of inertia, J. Because the brain has a somewhat spherical shape, and as a whole is a solid shaft, we will solve for J using the solid shaft formula, which is polar moment of inertia equals pi multiplied by r to the fourth power divided by 2. Gray matter makes up the outer cortex, which has a longer distance from the center with a larger radius than white matter does in the inner cortex. For an example calculation to compare the different distances, the gray matter will have a larger radius of 0.08 meters, and the white matter will have a smaller radius of 0.07 meters. The gray matter radius of 0.08 meters is plugged into the polar moment of inertia formula, resulting in an answer of 6.43 times 10 to the negative fifth meters to the fourth. To determine the white matter's polar moment of inertia, plug its 0.07 meter radius into the equation for an answer of 3.77 times 10 to the negative fifth meters to the fourth. With the polar moment of inertia for both gray and white matter, shear stress can finally be calculated. Say that at the moment of impact, gray matter has a twisting moment of 3,000 Newton meters. We can then multiply the 3,000 Newton meters twisting moment by the gray matter radius of 0.0 meters and divide that all by the polar moment of inertia. The shear stress of gray matter comes out to be 3.73 times 10 to the sixth newtons over meter squared. The same calculation can be done to discern the shear stress of white matter. Because white matter is located closer to the center, it will undergo less twisting, and therefore has a smaller twisting moment. If, at the moment of impact, white matter has a twisting moment of 2,500 Newton meters, that can be multiplied by the 0.07 meter radius of the white matter, and then be divided by the polar moment of inertia, to obtain a shear stress of 4.64 times 10 to the sixth newtons over meters squared. These calculations reinforce that white matter is capable of handling more shear stress than gray matter because it is stiffer. The consequences of a concussion can be examined in many different ways, from skull fractures to gray and white matter down to the last damaged neuron. It's vital that we take care of our brains and be prepared to protect it from any potential trauma. It is crucial not to ignore a concussion. Go to a doctor and get any kind of head injury checked out. After all, it's better to be safe than sorry.